All right, section 15.4 is chiral centers on a cyclical compound. Nothing has changed here, okay? This compound, it would be considered an achiral compound because technically this carbon right here has two of the same exact groups. So if you look at this direction, you have kind of a CH2, CH2, and you also have a CH2, CH2 here. So notice you do not have two different groups. It's kind of the same groups. Also, if your molecule has a plane of symmetry, then you know it's achiral. All right. So since you have two identical groups, this is not chiral. Therefore, this molecule is achiral. Okay. But when you get something like this, you now have four different groups. Here's our chiral carbon right here. We got a hydrogen, a methyl, a CH2, CH2, and then we got a CH and a CH attached to a double bond. These are different groups. So you have four different groups around that molecule. So this molecule is chiral. Okay. Why is it so important? Well, our whole entire body works off of this. Okay. Everything in our body works off of this chirality. Okay. Many biological active compounds contain one or more chiral centers. Everything we have in our body, okay, proteins, sugars, amino acids, our nucleic acids, they are all chiral, all right? And uh, even the way that our smell works, I'm sorry, not our smell, but the way that our smelling system works in our nose is based on chirality of the molecules, and we'll kind of show you an example of that. Okay, um, th this is the classic example. There's a drug called thalidomide that some of you might have heard of. It came out in the 60s. They used to give this drug to pregnant women to stop uh, morning sickness. But what was happening is when the mothers were giving birth to the babies did not have arms or legs, like their limbs were missing. They had this horrible name for them. They called them flipper babies. Some of you might have heard of this, some of you might not have heard of this, but this drug, again, was given, but as soon as those babies were being born, they stopped the drug immediately. And what was happening is that one of the enantiomers was stopping the morning sickness, but the other enantiomer was causing the birth defects. Okay, because it was sold as a mixture of the two enantiomers. That's called a racemic mixture. Now, your book does not talk about this, but I think being in the health field, this is kind of important because lots of drugs that are given are either in the racemic form or are in the one enantiomer form. Okay, and what pharmaceutical companies do is they have to test both enantiomers and make sure that they're both safe. Because it could be one of them cures cancer, but the other one causes cancer. That would be kind of an anticlimactic drug or a very non-productive drug where, hey, we found the cure for cancer, but yet the other enantiomer causes cancer. So, you know, it's a win-lose situation. All right. So obviously you would want to just give the one enantiomer that cures cancer. So this is kind of very important. Okay, thalidomide solar mixtures, both of which do not have the same biological effect. Obviously, one of them prevented nausea, while the other one caused birth defects in the unborn baby. Okay, so this is a classic example. This is the example everybody talks about when you talk about chirality. Here are actually the compounds. Here's the chiral carbon right here. All right, you can see there's four different groups. There's a nitrogen, a hydrogen, a carbon with a carbonyl, and then a CH2 group. Okay, this structure was perfect. It stopped morning sickness, but just because you have the other enantiomer, all right, caused the birth defects. Just by that, just to kind of show you, I find this fascinating how our bodies work. I mean, I don't find the drug, this whole thing fascinating, but as far as chirality and how our bodies explore this and how they just by changing one of the centers, it's the same compound, it's just how it differs in 3 dimensions. That's basically how our body works. Our proteins are these big gigantic molecules that fold in certain ways and have active sites. All right, it doesn't even matter what the amino acids are. All the amino acids are doing is folding them in a certain way so that they have active sites for things in our bodies in order to catalyze things, or like to make biological processes occur. Okay, so many drugs are chiral, and they often interact with chiral receptors inside our body. Okay, so one enantiomer of the drug may be effective treating a disease where the mirror image might be ineffective. Okay, if the other enantiomer is not biologically active, the pair is sold as a racemic mixture. Oh, there it is. I didn't think your book talked about it, but it does. Okay, so sometimes I think um, like either Tylenol or one of those are sold as a racemic mixture because one of them has zero biological activity whatsoever. So you can sell it as a racemic mixture. Just so you know, it's easier and cheaper to make and to synthesize a racemic mixture than it is like to make or to isolate just one enantiomer. Okay, because one, you lose 50% of your product if you just need to isolate one of them and sell it. And secondly, if you want to synthesize just one of them, all your reagents have to be chiral. So you have to start with very expensive reagents. So it's a lot better for, or more cost effective for pharmaceutical companies to sell racemic mixtures. All right, so a racemic mixture is equal mixture to two enantiomers. We've already talked about that. So here's a perfect example. Here's a phenylalanine, which is an amino acid, and let's say you have a chiral receptor. Okay, this is an old classic, like kids game where you have to fit the square block in the square hole and the round block in a round hole. That's basically how our bodies work. It's pretty interesting. So imagine I have a receptor site. This is the one enantiomer. All right. This site right here, this square site, is a perfect fit for an aromatic ring. Notice it has kind of a square shape, so that perfectly fits there. You have this one little hydrogen that fits perfectly in the diamond spot, and then you have the carboxylic acid group that kind of has an oval shape, and it fits in the oval spot. So everything here fits here. I got my square to square, my circle to circle, my triangle to triangle. If you have the other enantiomer, notice things aren't matching up. Okay, notice my triangle is able to fit in the triangle, but because I have the mirror image, I have my square aromatic ring on the opposite side. Obviously, I can't fit my square in my circle and my and the oval inside of the square. So things are not working here. I can't make this work. So that's why the enantiomers really have no effect or do not fit inside of a receptor site. So it's a great example of showing why our bodies are very specific as to the shapes of the drugs and specifically the chirality of the drug. Okay, so here it is. Ibuprofen was the one. So ibuprofen, obviously, you take for pain killing. It's also really good at anti-inflammatory. It's sold as a racemic mixture because the one enantiomer is completely inactive inside our bodies. Okay, but the other enantiomer is the anti-inflammatory and the painkiller. Now, just for your information, I want to kind of let you know what pharmaceutical companies do. Okay, obviously, they overall, they want to help people. Okay, but they also want to make a lot of money. Okay, let's just be honest. Now, it's a pretty it's an industry where you can make a lot of money, but you can also lose quite a bit of money. Okay, because if you are researching a drug, okay, and if you get a patent on that compound, you have 20 years for a patent on that compound. However, if you patent the compound at year one of your research and development, it can take anywhere between 15 to 18 years before that drug goes on the market. Okay, it's not like they find a drug and the next day it's on the market. It takes lots of time. It has to go through all the trials, has to get approved, you have to synthesize it cleanly and you have no waste. There is tons and tons and tons of man hours and money involved and time, and it can be anywhere between 15 and 18 years, and a pharmaceutical company wants to make a good profit. So they've spent millions, millions and millions and millions of dollars, right? Maybe even hundreds of millions of dollars just to get this drug in the market over the 15, 18 years. Well, they want to get their money back, plus they want to make more money on top of it. Okay, but they only have another 2 to 3 years or 2 to 5 years on their patents. Okay, and then their patents are going to be due, and then at that point, any pharmaceutical company is able to synthesize a drug and sell it. Okay, and they can sell it for a lot cheaper because for them it's pure profit. They don't have to pay for any of the R&D. So what pharmaceutical companies do is they get a patent, especially ibuprofen, because you can sell it in the racemic form. So they sell it in the racemic form. Then after the patent is due, what they do is they come out with extra strength. You've always heard of extra strength whatever. And what the extra strength is it's not a different compound. All it is it's just this enantiomer. What they do is just isolate this enantiomer and they sell 100% of enantiomer A. They no longer sell it in a racemic mixture and they call it extra strength. Well, why is it extra strength? Let's say you take 200 milligrams, okay, of the racemic mixture. 200 milligrams of the racemic mixture. Well, how many milligrams of the active compound are you actually getting? Well, you're getting half of this, right? Because the racemic mixture is both of these, but only one of them is the active compound. The other compound does nothing. It goes into your body and it goes out. Okay, so in reality, all you're getting is 100 milligrams of the actual compound. So even though you're taking 200 milligrams of the racemic, only 100 milligrams of it is the active component. Well, now let's say you have just 100% of this and you now take 200 milligrams of it. Well, now how much of this active compound are you getting out of the 100%? Well, you're getting all 200%. I'm sorry, 200 milligrams. Okay, so it's extra strength. I'm taking the same amount, right? However, it's working twice as good. My goodness, this stuff is extra strength. It's great. It's no different. It's the same exact thing. It's just that it's the one enantiomer rather than being sold the racemic mixture. So a pharmaceutical company can actually extend or get another patent on that drug, not for another 20 years, I think maybe for another 5 to 10 years, but they are able to patent the extra strength. So now, 5 to 10 years later, when the patent's due in ibuprofen, all the other companies are selling just regular ibuprofen, but now you're selling extra strength ibuprofen. Oh, hey, I want that instead. It works twice as good. All right. So that's kind of, so anytime you see things like that, like it's the new and improved, it's the longer acting, it's the stronger, all they're doing is just selling you one enantiomer. All right. So that's kind of the inside scoop of pharmaceutical companies. And again, I don't think it's anything wrong with it. Again, so many people have problems with the pharmaceutical companies. They have kind of geared towards trying to really be purely profit making because there aren't a lot of drugs that are coming out or being approved nowadays, so they have to extend the patents they currently have. But they still do a good job. I mean, ibuprofen, if you got a fever or you have a child that has a fever, 102, 103, 104 degrees, you do not want them to have a fever that high. You give them ibuprofen and boom, it knocks it down. I mean, it's still a great thing. It's probably saved a lot of lives itself. Naproxen, known as Aleve, in this case, there is no extra strength because the one enantiomer is a liver toxin. So they definitely do not want to be selling a racemic mixture. They sell exclusively the one enantiomer. All right. Interesting thing though is if you look, it's very similar. I think the same company made naproxen. Again, I think what they did is they sold ibuprofen. Once the extra strength was off patent, they came out with a new compound, naproxen. If you look, notice we have a carboxylic acid, a methyl group, and an aromatic ring. Notice naproxen, carboxylic acid, methyl group, and an aromatic ring, but you have an additional aromatic ring with an OCH3. It's very similar. Well, it does basically the same thing as ibuprofen. There are people that swear by this. This works better than the ibuprofen. Ibuprofen works better. Again, it just all depends on your active sites in your body and how the molecule affects or how it attaches inside of the active site. All right, another compound that's been shown is Ldopa. There's a great movie with Robin Williams called Awakenings, or Great Awakenings, it's something like that. It came out, man, I think I'm dating myself. Of course I am. I think it came out in the 90s. It was with Robin Williams. He was a doctor, and and it's based on a true story, which is actually really interesting. This was a doctor back in the want to say the 40s or 50s or maybe in the 60s. He was working with patients that had Parkinson's. All right, and he went to a conference and they were talking about Ldopa and how it interacts in the brain, and they, figured that Parkinson's basically is an interruption or the or the stopping of our dopa receptors inside of our brain. And what he was thinking is like, what if they took Ldopa, which is, like the chemical of our dopamine or a precursor of dopamine? If you take that, wouldn't that go into our bodies and kind of, fuel more of the dopa? And sure enough, it worked. And I recommend this movie. It's a fascinating movie, especially if you're going into the health field, because it's based on a true story. And I believe it's called Awakenings or Great Awakenings, and Robin Williams is in it. And it's a great movie. That's kind of the history of Ldopa. It was a drug that was found, again, I can't remember if it's 40s or 50s or 60s, it was somewhere around there. So if you notice, it's a very similar structure of dopamine. I'm sorry, I think we'll see the structure of dopamine in here. Yeah, we'll see here. But dopamine cannot be directly taken by a patient because it does not cross the blood-brain barrier. So here's dopamine. Okay, the reason it won't cross is because this is, I think, a little bit more polar. But Ldopa, you can see, is it just has an extra carboxylic acid group on it. Once it gets into the brain, that carboxylic acid group is knocked off, and then you start producing dopamine. Okay. So you can kind of see, so basically how dopamine works is you have a nerve cell, dopamine is released, it goes into the receptor sites and it activates, our brains, our pleasure activation inside of our bodies. It makes us happy. So it says that dopamine is released by one nerve cell and then binds to a receptor site in the target cell. In Parkinson's, however, you have a degeneration of the dopamine nerve pathway. Okay, so this area right here, you kind of starts, breaking down. So what the theory was is, what if you just pump the patient with dopamine? Well, it doesn't cross into our brains. If you take it, it just goes out of our urine. So what this doctor found is that Ldopa actually works very well. If you take Ldopa, it can cross into the blood-brain barrier. It acts as dopamine, and it seems to bring a lot of the Parkinson patients out of their catatonic states. All right, like I said, it's a great movie. You should watch the movie. All right, we're going to stop there, and we will come back with 15.6.